Welcome to Phase 3 of our Advanced Hero projects. Here we focus on self-healing Kubernetes clusters. This ensures total compliance and cost optimization.
When a production server cluster starts flashing red in the middle of the night, the standard response is a manual scramble to diagnose the logs. But notice how quickly this cluster snaps back to green. That resolution happened without human intervention. An AI DevOps agent detected a pod crash loop, identified the root cause in the logs, and triggered a rollback. Over the next 6 minutes, we are going to design that self-healing Kubernetes agent. We will map the architecture, define the safety rules, and generate the LangGraph code required to run it. To follow along, you only need 2 things: basic familiarity with your command line and access to an LLM workspace. Building these functional agents adds a layer of verifiable AI expertise to your portfolio. By the end of this guide, you will have a working system that moves from manual intervention to autonomous resolution of recurring failures. Before writing any logic, you have to establish the rules of engagement. Agents require strict environmental boundaries. You must define exactly how the system sees the cluster and how it is allowed to change it. We start with the input, an event watcher scanning the cluster for a crash loop back-off trigger. On the opposite end, we define the only allowed output tool, the rollback command. But there is a gap. Connecting these two without a diagnostic layer risks incorrect deployments. The LLM's role is to navigate the space between that trigger and that tool by applying diagnostic logic. Without explicitly defining these strict input and output boundaries, an AI agent cannot safely interact with live infrastructure. To bridge that gap, we drop in our LangGraph orchestrator. Step 1, the agent fetches the specific logs of the triggered pod. Next, it cross-references those logs against a historical runbook to find matches. If a historical match is found, it prepares the rollback tool. Breaking the diagnosis down into this rigid workflow ensures the LLM follows a repeatable, deterministic path to resolution. Even with a logical workflow, giving an LLM direct write access to a production cluster creates a risk of unintended service deletions or cascading rollbacks. We mitigate this with a human-in-the-loop checkpoint. The first time the agent encounters a specific incident signature, it halts execution and pings a human operator for approval. Once approved, the agent logs that error signature into a database as a verified resolution. The next time the agent sees that exact approved signature repeat, it bypasses the manual check and executes the rollback automatically. This learning safety boundary allows the system to scale its autonomy, moving from manual verification to automated resolution as its database of known signatures grows. With the architecture defined, we can move to the implementation phase. Look at this prompt on screen. By providing this architectural outline to an AI workspace like Notebook LM, you generate the Python code and function calling logic required to build the system. This master prompt provides the implementation guides and templates for 3 distinct projects: the Kubernetes agent, a compliance guardian, and a cloud cost optimizer. Using LangGraph and your cloud CLI, you can build these 3 tools to demonstrate a range of automated operations. As we can see on this resume, these projects allow you to provide data-backed evidence of your ability to engineer safe, AI-driven DevOps environments.